Welcome to the Teja Statistics. Today we are discussing about the randomized block design, which is short formally we are calling it as RBD. Definition: a method of dividing the heterogeneous experimental material into relatively homogeneous subgroups, or simply we can call it as blocks, stratas, and the treatments are applied randomly to the relatively homogeneous experimental units within each block and replicated over all the blocks is known as randomized block design. Simply in short form we are calling it as randomized block design. Yeah. For example, in agricultural experimentation, the experimental area or field is not homogeneous and the fertility gradient is only the one direction. Then a simple method of controlling the variability of the experimental material consists dividing the heterogeneous field into homogeneous subgroups or blocks perpendicular to the direction of the fertility gradient. So the then apply the treatments randomly to relatively homogeneous experimental units within each block and replicated over all the blocks. So here what they want to say, the definition: by doing the heterogeneous experimental units into relatively homogeneous, which we are easily we can identify that the column wise divisions, that they are said to be the strata. Sometimes we may call it as a blocks. So here the experimental observations within the units of each block is also be replicated over the number of times. So here this is called randomly selected, so that's why we are calling it as randomized block design. Yeah. Next, advantages and applications of this randomization. So randomized block design. Okay. So RBD provides more accurate results than CRD since the experimental material is divided into blocks. This results in decreasing the error variance. Yeah. Next, in RBD, no restrictions are placed on the number of treatments and on the number of replications, but at least 2 replications are required to test the significance of treatments or blocks. The statistical analysis of RBD is simple and rapid. The statistical analysis is simple even if the data is missed for any number of treatments. So this much of advantages are we required for this, and we have some disadvantages also. RBD is not suitable for large number of treatments since the block may contain more variability. Yeah, the column wise division. So next, the error may be increased if the interaction between the treatments and blocks exist. So the error may be increased. Okay, interaction between the treatments and the blocks. So by applying the treatments and we are dividing the total whole population into the blocks and treatments, then we may get some error, and that should be increased by applying the RBD. In every type of experiment, blocking or grouping is not possible. Okay, every time of the classification is not possible. Okay, in column wise applications of RBD. RBD is most useful in the field experiments like agricultural, environmental studies, etc. Next, the layout of RBD you can see here, the blocks 1, 2, 3, 4, and the treatments are here. We may repeat it so many number of times that repeated observations may occur. Okay, so here if you observed the treatments as A, B, C, D, E, and they are divided into the blocks. Okay, so this may be the uh, layout of the RBD. This will be looks like, just have a look over here. The layout of RBD is good enough to explain the through an example. In agricultural experiment, if we consider 6 fertilizers, we are naming it as fertilizers, and they are the treatments, okay, are applied and replicated 4 times. Okay, here the repetition is allowed up to the 4 values. Okay, then we divide the whole experimental area field as divided into 4 relatively homogeneous blocks, and each block consists of 6 units. Yes, 6 fertilizers, 6 units. Okay, are to be applied randomly to all 6 units within each block, so that a treatment should be replicated 4 times. Let the treatments are A, B, C, D, E, F. Okay, then the layout of RBD can be explained as follows. Okay, to allocate the treatments randomly, we use one of the method, lottery method or random number table method. Yes, for example, the selected units of the first block 2, 3, 4, 1, 5, 6. Yeah, you can see that 2, 3, 4, 1, 5, 6. Yes, similarly, then apply the treatments A to plot B, and B to plot 3, and C to plot 4, and D to the plot 1, and E to the plot 5, and F to the plot number 6. Like that you can apply each and every. Similarly, units are selected for all blocks, and then the treatments are allocated accordingly. That a very simple and easiest classification here. Yeah, just look at the statistical analysis of the RBD. The statistical analysis of RBD is similar to the ANOVA for two-way classified data. The linear mathematical model becomes Yij is equals to mu plus alpha I plus beta j plus epsilon ij, where I can take the values from 1, 2 and k, and j can take the values from 1 to h or n. We can substitute. Here they are considering j values from 1 to h. Okay, capital N is equals to n into k. Sometimes some people may take. Okay, mu is the general mean effect, alpha is the effect due to the ith treatment, beta j be the jth block. Okay, effect due to the jth block. Similarly, epsilon ij also we have. Okay, so k, h, and here G is a grand total. Yeah, Ti dot the total of formula, and y bar of I dot is a mean formula due to the ith treatment, and y bar double dot is a general mean formula. You can see. Next we have the total sum of squares model, that is TSS is equals to SST plus SSB plus SSE. The total sum of squares formula, and sum of squares due to treatments formula, sum of squares due to blocks formula, and sum of squares due to error formula we have. So null hypothesis, here we are testing that all the treatments are alpha 1 alpha 2 we are denoting, and equals to alpha k. All the treatments effects do not differ significantly, because we are assuming that they are all equal. Okay, beta 1 beta 2 are also do not differ significantly, that is they are also be the block, also be the equal performance they are giving. Next the statistical f calculated values. Here we can see f of t for the treatments k minus 1 into k minus 1 into h minus 1 total. Next sum of squares due to treatments SST divided by k minus 1. The mean sum of squares also we can for the calculation for the errors, so which is very similar to ANOVA two-way classification. Conclusion also you already know, if f calculated is greater than, we are going to reject. If f calculated is greater than for the treatments and blocks, we may reject the H0. Here you can see ANOVA two-way classification table. Once again, source of variation, sum of squares, degrees of freedom, mean sum of squares, and f ratio. Okay, very simple and easiest. Next, the least squares estimates we are going to learn in the next session. Thank you.